Hi everyone. So this video is on integration, C4 integration. Um, we're just gonna go through loads of examples of integrals, okay? Because we've done our video on Dijkstra's. We've got our tracking test coming up straight after reading week, and I want us to be ready, right? So you can do this in two ways. We did the mini integral marathon. We still haven't done two things called substitution and by parts. That's on the scheme of work a bit later. But for now, you've done that mini marathon. You've had a go, and that was the mini marathon was just trig changes, using your identities and kind of standard integrals, always differentiating to check. But now we've done partial fraction integration. You've got your fractions, your list, which hopefully you know. So when you're integrating a fraction, really important that you know your list, know your toolkit. So first was learn, wasn't it? Then it was reverse chain. So we don't waste time doing stuff we don't need to do. Reverse chain, then we've got factorize, don't we? Then we have long division, and then we have partial fractions. Okay, so, and obviously within here, there may be just simple trig changes first, because partial fractions doesn't apply to trig stuff. So here's what I suggest. I suggest you try each and every question as I go. You pause the tape, let's say per slide, pause the tape, you try all three, then play the tape and see if we do the same thing. Right? So loads of examples. We'll just do as many as we can until the 15 minutes, 20 minutes hits. Okay. 3 tan squared. Can't do anything with 3 tan squared by itself, but we do know some identities involving tan squared, don't we? And if you don't know where they came from, remember cos squared x plus sine squared x is 1. So if you divide everything by cos squared, so if you divide everything on the left by cos squared, you have to divide everything on the right by cos squared. So sine squared over cos squared is tan squared, plus cos squared over cos squared is plus 1, and 1 over cos squared is sec squared. So we can say straight away from here that tan squared x is sec squared x take 1. And it doesn't matter what the angle is. If that's a 3, then that's a 3. If that's a 4, then that's a 4. It doesn't matter. So this 3 and then our tan squared, because nothing differentiates to tan squared, but something does differentiate to sec squared, we can change this to sec squared 4x take 1 dx. Now my tip to you is to leave constants on the outside and times at the end. So don't worry about that 3. We'll leave that 3 on the outside. Sec squared 4x, well tan 4x would differentiate to sec squared 4s, but a 4 would pop out. So we need a quarter minus the 1 goes to x, and then let's not forget our plus c. So that's 3 by 4 tan 4x minus 3x plus c. Happy with that? So that was our guess. And now we could differentiate to check. And yes, we do get the 3 sec squared 4x minus 3 as required. So we're happy. So I would always box off my final answer. That's important, boxing off your final answer. Next one. Integrating 4 sine squared 3x. Again, think about that differentiation table. Bring that 4 on the outside. Nothing differentiates to sine squared. So we need an identity here. Again, I'm trying to get you to remember, you must remember that sine squared and cos squared you can't differentiate, you can't integrate, but you can. Only if you use an identity though. So we know cos 2x, for example, I'm just reiterating where this stuff comes from, you're more likely to remember it, is 1 minus 2 sine squared x. So if you know that, we can rearrange to make sine squared the subject. So if we move the sine squared x over, and move the cos 2x over, if you divide by 2, sine squared is a half minus half cos 2x. So sine squared, half minus half cos 2x. Likewise though, cos 2x is also 2 cos squared x take 1. So again, if we move the 1 over and divide by 2, we get cos squared x is half plus half cos 2x. I need you to remember these identities. See, everything's identical. Cos 2x, half, 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 half. The only thing that's different is the sign. So we know this is 4 sine squared 3x. If this was 2x in here, then the angle would be times by 2. If the angle was 3x here, the angle would be, again, doubled, so 6. If this was 4, this would be 8. So here we've got sine squared 3x, so this is half, subtract half cos 6x dx. And now we can integrate this no problem, so that's half x minus 1 over 12 sine 6x plus c. So your final answer, 2x minus 1 over 3 sine 6x plus c. Remember, that's your guess, and then you would differentiate to check. You must check. Do you get what you started with? Yes, sine does differentiate to positive cos, and therefore the minus is correct. So we're happy with that. Integral of 4 tan 2x. Again, I would take that 4 on the outside so I don't have to worry about it. Nothing differentiates to make tan, does it? So I hope you've paused this and you're thinking about it. Tan. What makes tan? Nothing differentiates tan. Can I use sec squared? No, because only tan squared is connected with sec squared. Nothing I can do. Nothing. Except, well, maybe go back to my original, what is tan? Well, tan is sine over cos, isn't it? Now you've got a fraction. So we're back into our fraction list over here. How can we deal with a fraction list? Well, we start off with ln. Does the bottom differentiate to the top? Absolutely. Because remember, ln f of x differentiates to f dash of x over f of x. Not f of x over f dash of x. F dash of x over f of x. So does cos differentiate to sine? Yes, it does. So I would guess, you could put g here if you want. So the 4 stays. Ln cos 2x. Oops, cos 2x plus c. And I would need to differentiate this to check. It's not very clear. Let's extend this. Equals 4 ln cos 2x plus c. Multiply out 4 ln cos 2x plus c. So now differentiate to check. Cos 2x. So ln f of x goes to the f of x on the bottom, as we've said. Cos goes to minus 2 sine 2x. All times by that 4 gives me minus 8 sine 2x. So it's too big, isn't it? It's too big, and there's a minus in there. So I need to divide everything. If I divide this by a half, well, times it by minus a half, then I need to times my original by minus a half. So actually my adjusted one, so the GDA is minus 2 ln cos 2x plus c. And box that final answer. And if you differentiated it, you would get what you wanted. Let's keep going, let's keep going. So, again, try this by yourself. Write this out properly. We've got what looks like a fraction. So, going through my list, does the bottom differentiate to the top? No. Can I use reverse chain rule? No. Can I therefore use long division? Well, factorize, sorry. Can I factorize this? Well, the top 3x, x, 2 and 1. Does it factorize 2 and 1? I don't think so. I don't think it does. It definitely doesn't factorize with an x minus 1 and x minus 2 to cancel. So we've got to use our next step, long division. Is it long divisionable? Yes, because the bottom, if you multiply it out, the powers of x are the same. So powers of x same or bigger in the numerator, therefore long division. So make sure you're noting this to yourself. If you want to be good at C4, you have to be able to integrate, okay? It's all about integration. So I'm going to forget the integral sign for now, use our slick method, write the bottom and top on the top, w here to the side. What do I need to times x squared by to make the 3x squared? Well, I need to times it by 3. If I multiply that out, that's 3x squared minus 9x plus 6. 3x squared is good. Got a minus 9x. Everything else is a remainder. I need a minus 3x, so I need to plus 6x. Got a plus 6. Need a minus 2, so I need a minus 8. And now that's the same as, well, I can write it long if we want, over x squared, take 3x plus 2, plus, and now your remainder over x squared minus 3x plus 2, and therefore that bit cancels. So 3 plus 6x take 8 over x squared minus 3x plus 2. We know it doesn't factorize, so we're going to go straight back into our denominator, x minus 1, x minus 2. Keep going through your list. Is it learnable? No. Is it reverse chainable? No, because remember we're integrating this still. Go through your list. Long division, we've already done that, so now we've got to use partial fractions. And this is now a case 1 situation. So what I would do is I would asterisk that off to the side, forget the integral for now. And partial fraction questions are long, but you should feel happy when they arrive because you can check everything. You know whether you're right. So like before, if I wanna, I'm always comparing this one with my denominator. So this one is missing an x minus 2. This one is missing an x minus 1. And now I can put the denominator together, and now the bottom equals the bottom, and therefore the top equals the top. So 6x take 8 is the same as ax minus 2 plus bx minus 1. Let x equal 2 to get rid of this bracket here. So therefore 6 times 2 is 12, minus 8 is 4. That one's gone, and therefore you're left with b. Also, let's let x equal 1. So going through quickly now, minus 2 is minus a, so therefore a is 2. And let's write out our integral then. So 3 stays, plus the a, which was 2 over x minus 1, and our b, which is 4 over x minus 2. And then we've got our dx on the side. And now we can integrate this no problem. 3 goes to 3x, plus 2 ln mod x minus 1, plus 4 ln x minus 2, plus c. But I shouldn't have done that at all, because I hadn't checked. So let's prove how quickly we can check this. If I whack 0.01 in there, you should be doing this at the same time. Remember, 70% of C3 is integration. So this is absolutely not a waste of time. You should be doing all of these integrals either with me or looking at how I'm doing it if you're not matching the same answer as me. So I get, if I put in the right hand side this, hopefully you agree. See how quick you can do this? So, and then put it into the original. So when I say the original, I mean this one. Does that match? So 3 answer squared using 0.01 minus 3 answer minus 2. So in the top, 1, 3 answer 2. And we get exactly the same thing. So we're happy. Cool. Right. It's always nice to know with partial fractions that you're guaranteed to be correct. That's nice. Second one. Fifth one, sorry. Right. This is one that people, I noticed in the mini marathon, found really difficult and didn't react to enough because we're not going through our list. So ln, is it ln? No, it's a fraction. Is it reverse chain? Well, it could be. So what do I mean by reverse chain? You can only put this in reverse chainable form if you bring up the 3x minus 4. So you make that to the power minus 3, and that's where most of you were going wrong. You weren't bringing it up. Now you can look at this like a regular reverse chain rule problem. Is the differential of the inside out here? Yes, or in some form, because 3x would just go to 3. So immediately we are adding 1 to that power and dividing by the new power. And the 4 is still present, so we've got 4 over 2 there, plus c, remember? So at the moment, I've got 2, 3x, take 4, minus 2, plus c. This is our guess. We must differentiate, because it's always tricky getting these ones right. So if I differentiate, the minus 2 would come down, so that makes minus 4. 3x minus 4 to the minus 3, see? So the power has changed. And then the 3 would pop out, because that would be the differential of that. So I've got minus 12, 3x take 4 to the minus 3. We, though, started with a 4, not a minus. So if I times this one by a minus, then I need to times this one by a minus. And if we times we've got 12 and we need a 4, so if I divide this one by 3, I need to divide this one by 3. So that was my differential there. Made that a bit trickier. Let me go back over that. So the minus 2 comes down, so that's 4. Ugh. Can I go again? Sorry, folks. So this is 3x minus 4 minus 2 plus c. Okay. That's what we think it is. We'll differentiate it. The minus 2 comes down, so 4, 3x take 4 to the minus 3 times 3. So that brings us minus 12, 3x take 4 to the minus 3. This one needs to be times by minus 1, so therefore this one needs to be times by minus 1. This one needs to be divided by 3, so therefore this needs to be divided by 3. And that's our adjusted answer here. And if you differentiate it, does it work? Yes, it will work. Okay? So you can differentiate and adjust as many times as you need to. Let's keep going then. So this time we've got x squared over 2x cubed plus 3 all squared. Looks horrible, doesn't it? But let's go through the motions. Is it ln? Does the bottom differentiate to the top? Nearly. We will get a 6x squared, but the problem is that 2 here. The 2 would come down, wouldn't it? And reduce the power to 1, and then out would pop that 6x squared. So it doesn't match the top. So this is not a ln, but failing that, we go to reverse chain. How do we go to reverse chain? Like before in a fraction, you need to bring the fraction up. Now, is it reverse chain? Does this inside differentiate to x squared? Yes, it does. So straight away, we isolate that element where we recognize that's the case. We plus 1 to the power and divide by that new power plus c. So at the moment, this box is my guess. Now I'm going to differentiate to check. The minus 1 would come down, so that would make 1. So that's 2x cubed plus 3 to the minus 2, and then out pops a 6x squared. We don't want 6x squared, we just want x squared. So if I divide that by 6, I need to divide this one by 6. And there we go. We've got our answer. Differentiate it to check quickly, and we're happy. Let's keep going. So, integral this time. This is I really think this is a helpful video for you folks, because you need to get good at integration. And the more you do, the more you'll see what to do. So this is a trig one. So the ln and the reverse chain rules apply, but the partial fractions and long division and all that doesn't apply. So it's either going to be change some identities up, or it's going to be a ln or reverse chain. Straight away, I can see that 1 plus sin x doesn't change to anything, and neither does cos. But I also can see that if I split this up into 2 sections, this is now looking very much like something that I can integrate. Plus, and now sine over cos is the same as tan, but that doesn't help us. And we already did tan earlier, and with experience, I can see that we want to look at this like a ln. So what is the integral of sec x? Well, this is a difficult one. This is actually a standard formula in the formula book, and it does go to ln sec x plus tan x. If you differentiate that, you will get sec x. And then here for your tan x, we get cos x on the bottom, so that's ln cos x plus c. And if you differentiate cos x, that goes to minus sin x, so we'll have to change that to a minus there. Okay, now that sec x one, why is that? Google it. You know, Google it. Do I have to tell you where everything comes from? Not really. I think that you guys are capable of Googling that. But if try it, differentiate it to check, make sure that sec x does integrate to that. This one here. Now, if you know your formulas, you'll recognize that this is a sine and a cos, but different angles. So this hopefully is making you think, sine p plus sine q. And sine p plus sine q is the same as 2 sine p plus q over 2 cos p minus q over 2. So what we need to do is we need to find out what p is and we need to find out what q is, because we can't integrate this at the moment. So this is using the factor formula. Okay, factor formulae. So really helpful formula to have. We've got the 2, so we can see that 4x is the same as p plus q over 2, so therefore p plus q must be 8x. Can you see? We can see that 3x must be the p minus q over 2, so p minus q over 2 is our 3x, but if we times up by 2 we get 6x. Do you see? I hope you see where that's coming from. Now it's just standard GCSE elimination. If we add these two together, can you see the q's cancel out? 8x plus 6x is 14x, is 2p, so p is 7x. If we minus them, 8x minus 6x, that's 2x. So p take p goes, and q minus 2 minus q is 2q. So therefore q must be just x. So now we're integrating sine 7x, there's our sine p, isn't it? Sine p, and then sine q plus sine x, which is our q, and now we can integrate this no problem. So that's a 7x plus cos x plus c, that's our guess, but is that right? Well, if I differentiate it, cos goes to minus sine, so therefore this is a minus, and this is a minus, and we're done. Might as well do a couple more then. Remember, this is all good for you. And integration, I think, is really fun. And if you don't think it's fun, you are in totally the wrong place. Because C4 is all integration. Go through our list again. This is classic problem where people don't get this right, and it's because they don't go through the list. Is it ln? Does the bottom differentiate to the top? The inside does. But we've got this 3 here, so no, we can't use it. Reverse chain. Can we reverse chain it? Maybe. Let's bring that up then. Remember, in that fraction, we always need to bring it up. Does the inside of this differentiate to this? Absolutely. So we isolate that section then in reverse chain. Whoops. We'll leave that. You can leave the constant on the outside if you want. It literally doesn't matter, because every time you're going to check and adjust. So 1 plus tan x plus 1 to the power divided by new power plus c. That's our guess. But if I differentiate it, the minus 2 comes down. So that now makes 1 plus tan x to the minus 3. But we want, and then the differentiate the inside, the sec squared comes out. But we need a 3 there, so we need, if we times this by 3 to adjust, we times the top by 3, and now we're happy. Number 10, this time 2x squared e to the x cubed. Whoa, looks like a beast, doesn't it? We got an e to a function, so immediately e to the function. Well, what does e to the function differentiate to? Well, that's f dash of x e to the f of x. You see how important your identities are to make you spot stuff, i.e. I see an e to the f of x, so I'm straight away thinking, is the thing next to that the differential of this? Yes, absolutely, pretty much. So I go straight into e to the f of x plus c is my guess. If I differentiate it, e to the f of x goes to f dash of x, e to the f of x, so that 3x cubed goes to 3x squared, e to the x cubed, but we need a 2x squared. So we need to divide by 3. So here I would divide by 3. If I do that in my adjust, in my differential, I need to do it in my guess as well. And I need to times by 2. So I times by 2, and we're happy. Could keep going. You guys can do this by yourself if you want, but I think you've listened to me long enough. Have a go.